probably could have included this on the last video. I think there was enough time, and this is not too complicated. We saw this in lab, talking about clearance. Clearance is a non-invasive way to assess renal function. Clearance has that weird definition. It's the volume of plasma cleared of a given solute in a given amount of time. The units for clearance then, since clearance equals UV over P, so U is the urine concentration, so that's measured in often milligrams per milliliter, but it could be measured in anything. The P is plasma concentration. That's also in the same units, milligrams per ml. So those are going to cancel each other out. So what we're going to be left with is that V, the V is the urine production rate, which is typically in mLs per minute. So the clearance is in mLs per minute. And so it's kind of weird because we're always often thinking about removing things from solutes from liquid as opposed to liquid from the solutes. And the way we can do that physiologically is through filtration. So that's one of the key components there. So that is a basic definition of clearance. So for clearance, one of the things we do is when we do the calculation for clearance, the UV over P calculation. And again, for the lecture portion of the exam, you will probably have to memorize the equation, right? So I just remember that little word in my head, the little rhyme, UV over P. So for any substance that's freely filtered, which means it gets filtered through the glomerulus. If you remember, kind of use this to review some things, the glomerulus is a much more permeable capillary than other structures. And other capillaries. It's 100 to 1,000 times more permeable, yet at the same time much more selective, meaning it doesn't allow everything to go across. And its main selectivity includes proteins, they don't get across, and any of the formed elements. So there's no red blood cells, white blood cells, or platelets that also get filtered across. So if you have a substance that's not any of those, so it's freely filtered, and not secreted and not reabsorbed, then the clearance is equal to GFR. And so theoretically, in a clinical situation, we could take a substance that was freely filtered, not reabsorbed, not secreted, and measure the clearance of that, and that would give us what the GFR measurement was. Normal GFR, we said, was about 100 mLs per minute. So here's one of the things that we can look at. So we're going to assume for our course that if the clearance is 0, the substance was filtered. Just as an aside, if you look down here on the bottom right of this slide, if the clearance equals 0, it could be that it was never filtered, right? So the clearance of proteins would be 0. And the reason why is if you did the calculation for protein. So if you look at the clearance of proteins, right, clearance equals UV divided by P. So how much protein should be in the urine? Well, none, because it shouldn't be in the ultrafiltrate, right? So if this number is 0, it doesn't matter what V and P are, it's going to be 0. So if the clearance is 0, it could be that either the substance was never filtered in the first place, like proteins or your cells, or it was completely reabsorbed. So that substance was filtered originally, but then our body reabsorbed all of it. And so those two ideas, right, we'll just worry about and assumed everything is filtered. So we're not going to worry about this one. So I'm going to cross it out. And then for our purposes of class, we're going to assume that everything, right, everything is filtered for our purposes. So assuming it's filtered, then we can look at a couple situations. If clearance equals GFR, right, it tells us it was not secreted and not reabsorbed. Because if it was secreted, we'll see in a second, it'd be more than GFR, and reabsorbed would be less than GFR. And again, that would mean that substance was a good candidate to measure GFR. Now, if clearance is less than GFR, that means we have net reabsorption. It means that some of the material, as it moved through the tubules, was reabsorbed. Now, we've mentioned this before, but the primary portion of the nephron that handles the reabsorption of things is the proximal convoluted tubule. So we have net reabsorption in that case, and more than likely in the proximal convoluted tubule. Now, we could also have clearance that is greater than GFR. Now, if your clearance is greater than GFR, it says you have net secretion. That means that your body is taking things, right, from out of the blood and sticking them into the urine to pee them out. So that's net secretion. And if we're doing that, then we'll see the clearance go up higher than GFR. So our frame of reference, unless told otherwise, is we're going to assume that a normal GFR is accomplished by a person, which is 125 mils per minute. So if clearance equaled 125 mils per minute, if it equaled GFR, it would tell us the substance was filtered, not secreted, not reabsorbed, and it would be a great substance to use to predict GFR in humans in a clinical situation. If the clearance was less than GFR, it means we had net reabsorption and the material was being reabsorbed in the body. As an example, glucose has a clearance of 0 under normal circumstances because we would expect that all of the glucose will be reabsorbed as it moves through the proximal convoluted tubule. Remember that glucose is reabsorbed by protein transporters, and the glucose has a transport maximum of about 275 milligrams per deciliter. So once the glucose exceeds 275 milligrams per deciliter on average in someone's blood, that we're going to saturate those receptors, okay, and that's called the transport maximum, the point where they get saturated. So if we exceed transport maximum when we reabsorb substances, then some of that is going to spill over in the urine. So under normal circumstances, we don't expect to see any glucose in the urine. But in somebody with diabetes mellitus, we might see glucose in the urine because their blood sugar go high enough where it saturates the receptors and some of it spills over. So if we exceed the transport maximum, that'll happen. But that's true of vitamins and things like that. So maybe you decide that, hey, I'm going to try to boost my immune system, and I'm going to take 100 times the recommended dose of vitamin C because I think it's healthy for me. Well, the vast majority of that vitamin C is just going to be peed out because in the kidney, when it gets filtered in the kidney, you're going to saturate the receptors that pull vitamin C back into the body, and the vast majority of that will just end up getting peed out. So net reabsorption, right? The substance would have a clearance less than GFR. And the opposite is true for secretion. So if the clearance was greater than GFR, if it was greater than 125 mils per minute, we'd have net secretion. It means that our body is taking that substance and putting it into the tubules for eventual excretion through the urine. So let's see if we got anything else that's interesting here. So here's just an example of glucose and some of the numbers that we would see. Like I said, the units could be anything. So here, the example of the units are molecules per 100 mLs. But again, it doesn't matter what you have. This would be milligrams per deciliter. In Europe, they measure glucose in millimoles per liter typically. So, it doesn't matter as long as the U and the P units are the same. So using our basic equation, clearance equals UV over P. And we have a situation where we have 0 molecules of glucose in the urine, right? So 0 over here, that's clearance, sorry. No glucose excreted, this would be 0, right? Times 100 mils per minute, that's how much glucose is reabsorbed, divided by the 4 molecules per minute, and that would give me 0. Since the clearance of glucose is less than GFR, it tells me glucose is reabsorbed. In this case, since there's no glucose, it means it was completely reabsorbed. And again, that would be a normal circumstance that we would see the vast majority of people. Now, you could do a similar calculation for urea. And urea is something that you would think would be a substance we would want to get rid of. Urea sounds kind of nasty, and you'd think, oh, I don't want to get rid of it. I mean, I don't want to keep urea, I want to get rid of it. Well, if you're not sure, which we're not, as you'll see in a second, at least I wasn't when I first saw it. Let's say that the urine urea is 2 molecules per 100 mLs, the V is 100 mils per minute, and the P is 4 molecules per 100 mL. So the molecules per 100 mL cancel out. So we get 2 times 100 is 200. Divided by 4 gives me 50 mLs per minute. So we maintain the units, right? So 50 mLs per minute. So basically, since the clearance is less than GFR, we can say that urea is actually reabsorbed. Now, it's not completely reabsorbed, because if it was, it would have a clearance of 0, like glucose, but it's partially reabsorbed. And in fact, you would argue that anything less than 125 would be partially or completely reabsorbed, and anything above 125 would be partially or completely secreted. Now, here's an example of penicillin. Penicillin is considered by the body as a xenobiotic. Remember, xeno is foreign, so it means a foreign substance. And so it's hard for humans to keep penicillin in a high concentration in their blood, actually, because it's actively secreted. So for penicillin, we'll just take some numbers, and this will be 6 molecules per 100 mLs, and the plasma was 4 molecules per 100 mLs, and that production rate we had is still 100, even though it's excessively high. So we get 6 times 100 is 600, divided by 4 is 150 mils per minute. Since the clearance of penicillin is greater than GFR, 150 is greater than 125, it tells us penicillin is secreted. So practice with clearance and know how to calculate it. Make sure you understand the hormones and the difference between the 3 water conservation hormones and the 1 water excretion hormone. Make sure you understand about the functional anatomy of this. Make sure you understand about the Starling forces and how they help to maintain GFR. And then, of course, probably the most important one, how does the human body homeostatically regulate GFR and maintain normal glomerular filtration during the day. So that ends our series of videos, I believe, on the renal system.